Remember, in our simulation, sodium conductance was 0, potassium conductance was non-zero because of resting channels, so it was slightly above potassium. And then what happened when we applied stimulus? We depolarized the membrane a little bit, and that depolarization caused sodium conductance to increase, and it overcame potassium conductance. So that's the point we call threshold. After that point, sodium channels start to open independently on your stimulation current or on your synaptic inputs. You already reached point of no return. Sodium channels will provide depolarization, which will provide drive to open, which provide more depolarization, so it's positive feedback. Without counterbalancing negative feedback, you go to the maximum. And the maximum means all channels open. Okay, so coming back to our question, what will happen to sodium channels during this? Will they open? Will they not react? Will they close? Or will they open and then close?
They open, then close.
Okay, so far it became clear why they open, but why do they close? Why do we have decrease in sodium conductance? Remember, in activation, this is important. All sodium channels, voltage-gated sodium channels, have the property of inactivation, and that makes sodium conductance go down. If potassium conductance was just at the same level as it was before, and it wasn't changing, what will happen to membrane potential? At this situation, we have a rapid decrease in sodium conductance, and it becomes 0 again, the same as it was before. But potassium conductance is still higher, so the fiber will repolarize, but that repolarization will be slow because this conductance is small. What happens in reality? We have voltage-gated potassium channels in addition to background potassium channels. So this does not stay flat, but increases. But that increase takes time, and the curve of increase is much more sigmoidal compared to sodium conductance. And this is because for potassium channel to open, there should be 4 gates open in 4 subunits. Okay? So when one open, the channel is not conducting. When the second one open, the channel is not conducting. When the third one is open, the channel is still not conducting. So you need 4. However, when you have all channel gates closed, you have a long way to go to all 4 open. But if one is already open, you only have to open 3. If 2 are open, you only have to open 2. If 3 are open, only 1. So the probability is increasing as you open the gates. And that's why activation of this is like that. It's sluggish initially and then faster, faster, faster. But in sodium channels, we've got only 3 activating particles. So 3 gates have to open to provide full opening of M gates. I gave it to you as M gates, as 1 gate, but there are 3 components in sodium channel and 4 components in potassium channel. So that's why there is a difference, time delay, plus transitions between closed and open in potassium channel are slower than in sodium. Because of that, we have delayed rise in potassium conductance, and it becomes higher than sodium earlier within the action potential. So that provides more drive to repolarize and even to go closer to the reversal potential because we still have high potassium conductance. It will go down to pre-existing because when you repolarize, there is nothing more to open the channels. Remember, they will open if they are depolarized. Potassium channels. Sodium will open and then inactivate. Why it which is important to remember about inactivation, voltage-gated inactivation. That is because it determines the refractory period. For any neuron, it will dictate how quickly that neuron can generate bursts, series of action potentials. How quickly it will be ready to accept and generate second action potential. That's in neurons. In cardiac muscle, for example, if you have incomplete inactivation in sodium channels, that creates a lot of problems, again, of arrhythmias. So any abnormalities in sodium channel inactivation have potentially dangerous consequences in terms of arrhythmias. And unfortunately, indeed, there is a type of arrhythmia called long QT syndrome type 3, where there is a mutation in sodium channel, cardiac specific sodium channel, which makes that channel not inactivate rapidly, but inactivate slowly and incompletely. So that creates a problem. We will talk about that again in 3 years' time. All you need to know is to have a lot of respect to sodium channel inactivation, because this is important. Okay? And remember, it's there, and remember, it may go wrong with all the consequences. Okay? More questions? So this is the very basic scheme of synaptic transmission. I want you to remember for now, but also be conscious that this is overly simplified. In reality, it's a bit more complex. We will not go into complexities as now, but you will have central nervous system lectures, I think next year in Human Physiology 2. And you will see, or Human Physiology 3, more 3. You will see that presynaptic membrane is much more complex than just a source for calcium entry. It also has mediators, receptors, similar to these here, and that's the negative feedback. It has mediators to some things that is not directly related to synaptic transmission. For example, synaptic transmission in this particular synapse is achieved by acetylcholine or glutamate, and there are receptors here towards noradrenaline or 5-hydroxytryptamine. These substances will change how neuron behaves depending on their concentration in the blood. And that's what makes the nervous system extremely complex. All these extra levels of complexity. But you can only understand them when you understand the basics, the simplest scenario. Okay, so if there are no more questions, let's finish now. And I'm looking forward to next lecture to tell you more about cardiac muscle and smooth muscle in comparison to skeletal muscle. Thank you.